course Advanced Reaction Engineering. So, in this course today we will discuss about catalyst characterization techniques. So, that already we have discussed and already have started. So, in our previous class we already have discussed about the catalyst synthesis and catalyst characterization by using BT, surface area, pore size and pore volume. So, when a catalyst is better than other catalyst, if you do compare for a particular reaction, so then that catalyst, why one catalyst is better compared to the other catalyst. So, that may be various reasons. So, it may be we can characterize those catalysts by using porosity, pore volume, surface area, amorphous crystallinity structure, acidity, acidic and basic natures, thermal stability, redox properties, oxidation state, electronic structures or properties, surface morphology, elements analysis, vibrational characterizations and particle size and shapes. So, by that way we can characterize one particular catalyst why it is better than other catalysts. So, we can characterize those and by that way we can develop a new and better catalyst. So, many characterization techniques are available. So, here's just short summary individual characterizations why it is important and what kind of informations we can get from that particular characterizations that we will discuss. Here BT means specific surface area of that particular catalyst and pore size, pore volumes we can find out, that already have discussed. And now we will discuss about hydrogen TPR, CO2 TPD, ammonia TPD, chemisorption study, and then TGA, DTA, XRD, SEM-TEM, FTIR, Raman spectroscopy, UV-vis-NIR spectroscopy, XPS, GC, GCMS, these are the things we will discuss. Very shortly we will discuss. So, due to the time constraint. So, I think this is the equipments, it is micromagnetics equipments which is available for the hydrogen TPR, CO2 TPD, ammonia TPD and chemisorption analysis. So, let us say we have this catalyst, for this particular catalyst TPR analysis, TPD analysis and chemisorption study we want to do. So, then first we have to do, so we have to place the catalyst here and this is furnace and here to measure the catalyst temperature, thermocouples and controller is also there. So, here first we have to do the pre-treatment of degassing, step 1, and step 1 degassing means when the catalyst we have prepared we are storing that inside of an container. So, there it may get adsorbs moistures or CO2 from the atmosphere. So, before start the experiment we have to degas, that means we have to preconditioning or pre-treatments of that materials you have to do at a particular temperature, that may be 200 or 250 degrees centigrade by flowing of some inert gas. So, we have to place catalyst and then we have to pass argon gas at let us say 200 degrees centigrade for 3 hours. Then so all impurities would be removed. So, impurities will come out like this and vent is there, and after that we have to start in the second step. So, to conduct the TPR experiment. So, in the TPR experiments pre-treatments we have passed argon gas, now with hydrogens and argon mixtures gas will pass through this catalyst. So, once it passed through this catalyst and the temperatures that may be 25 degrees centigrade to 1000 degrees centigrade, let us say we can vary the temperature of this furnace and the catalyst temperature. Then hydrogens gas once will pass. So, hydrogens, in presence of this hydrogens in this catalyst there would be a reductions, means let us say nickel oxide is there our catalyst. So, this is our nickel oxide. So, in presence of hydrogens at particular temperature, means let us say 25 to 400 or 500 degrees centigrade if you reach. So, then so what would happen, this type of reactions would be there, means nickel oxide would reduce to nickel metals, these changes would be there and hydrogen consumptions would be there, means hydrogen gas will consume to reduce this. So, this would forms in the catalyst surface and hydrogen gas will adsorb. So, hydrogen gas, that amount would get adsorbed or the amount of the nickel oxide would be present. So, here TCD signals we can get from here y axis and x axis temperatures. So, this from this experiment, so here TCD signal means the amount of hydrogen gas consumed from to reach this temperature. So, this type of maybe curves would come. So, it indicates means the amount of gas at this particular temperature it is adsorbs means reacted with that surface of the catalyst. So, then here's for this particular catalyst, one catalyst was taken 70 and 290 degree centigrade, 2 peaks we observed. So, it means this peak, it may be due to the desorptions of physics of water molecules that was present get desorbs, and it may be nickel oxide or nickel sites that gets desorbs, means when hydrogen consumption is here more. So, that way you can say that. So, how much quantity of hydrogen gas means required to reduce that catalyst, at what temperature also that reactions will take place, that easily we can measure with the help of this type of experiment or temperature program reductions. Okay. Similarly, CO2 TPD also we can do carbon dioxide temperature program desorption study. Mainly with this help of this study we can get analyze the basicity of the catalyst, means if there is surface of the catalyst is there, if some basic natures is there, let us say the surface. So, then if we CO2 come here, so then CO2 get CO2 acidic natures. So, it would get adsorbed over the surface of the basic sites are present in the catalyst. So, if we quantify the CO2 concentrations, then number of basic sites also we can quantify. Okay. So, here is one example I have taken. So, here is MgAl2O4 in this catalyst. This is the TCD signals and this is the temperatures. If we go 100 to 800 degrees centigrade, first we have to take that materials in this experiment. We have to degassing the materials or the catalyst have to degas with the help of inert gas. After that, so we will pass CO2 and argon gas. So, then CO2 get adsorbs or adsorbs over the surface of the catalyst, and after that we start the desorptions. Once it get adsorbs, then if you desorb CO2, then how much quantity amount of the CO2 was adsorbed, with the help of desorptions the quantify, we can do the quantification of the CO2 that was adsorbed by the desorptions experiments. So, it has been observed that when temperature after adsorptions, when we started desorptions, then by rising the temperature 100 to 800 degrees centigrade, this type of natures of curves has come for this particular catalyst. So, at this 87 to 91 542 these temperatures means it indicate 3 different type of basic sites are available, weak basic sites, medium basic sites and strong basic sites are available for this particular materials. And this particular materials it is showing red dotted lines, so here it is little bit different. So, means one materials to another materials rate of means quantity that get adsorbed, that is different, and the desorption temperatures that also different. So, here 681 and here 542. So, here strong basic sites are available, but they get desorbed at 542 degrees centigrade. So, it is comparatively much more stronger basic sites in this particular catalyst it is present. So, that way we can also means classify or we can means analyze that two different catalysts and two different materials and their basic properties. Next is ammonia TPD like CO2 TPD. CO2 was the means acidic gas, it would give the basic sites in the catalyst. Ammonia is the basic nature. So, therefore, it would adsorb over the sites of the catalyst where acidic sites are there, acidic strengths or sites are available, there ammonia would get adsorbed. So, similarly, after adsorptions if we do desorb, so ammonia will come out from the surface of the catalyst. If we are able to quantify how much quantity of ammonia was adsorbed over the surface of the catalyst, then we can easily say that what the nature of the acidity or acidic nature of the catalyst and how much quantity of the sites are available. So, that easily we can quantify here. Red one was the calcium oxide. So, that was done by ammonia TPD. Here you can see up to 100 to up to this temperature 300 there is no adsorptions. So, desorption. So, after that desorption has started and up to this and then it is coming linear. So, 300 to 420 within that temperature range the ammonia that much quantity ammonia dissolves for this particular materials. Similarly, for alumina was also done, magnesium oxide also was done, so the ammonia TPD study. So, in that case also different nature of and different temperatures the ammonia get dissolved for that materials. So, one materials to another materials, the amount of the gas desorption is different and temperature is also different. So, means one catalyst to another catalyst, one materials to another materials, the amount of the acidic sites and strengths of the acidic sites are different. So, this type of things we can observe and observations we can conclude. And now the chemisorption study. So, similarly, so I said let us say catalyst is there. So, in the chemisorption study this is the nickel oxide. So, means these are the calls CT. CT is the total number of sites when a reactions we are conducting in presence of let us say any catalyst is there. So, these are the active sites. So, how many number of active sites are present? Means whenever we are synthesizing the catalyst, nickel oxide acts as active sites, but how many quantify? If you want to quantify, that may be thousands numbers, 2000 numbers of active sites are present per gram of the catalyst, that we want to quantify. So, how that we can do? So, if any catalyst the number of active sites are more, then the catalyst of course would be much more better than the catalyst having less active sites. So, here in this chemisorption analysis we can do that. So, for chemisorption what we have to do, similarly like hydrogen TPR, CO2 TPD, ammonia TPD. So, we have to take the catalyst in that equipments or inside of that sample holder, and then we have to do hydrogen treatments. So, if you do the hydrogen treatment, so it is nickel oxide, then it would be reduced into nickel metals, and after that if we, this is step 1, and step 2 nickel metals and nickel oxide would be converted into nickel metal. So, here you can see it very clearly, this catalyst was taken. In the step 1 we have conducted reductions, means nickel oxide, these are the nickel oxides. If we maintain let us say 500 degree centigrade for 3 hours in presence of hydrogens, these oxygens will be removed by interact with the nickel oxide, means nickel oxide plus hydrogens react with nickel metals and water it would form. So, these are the nickel metals, initially it was nickel oxide. So, then let us say this was our first step 1, the reductions. After that pulse chemisorptions of hydrogens would be injected in the sample holder. So, then the surface present, these are the surface where hydrogens once again injected in the sample compartment. So, hydrogens would be chemisorbed like this. So, how much quantity hydrogens that was injected and dispersed over the surface of the catalyst, if we are able to quantify. So, then we can find out let us say 2 surface sites. So, this so 2 surface sites, 1 hydrogen molecules occupied 2 different hydrogen surface sites. So, if we are able to quantify the hydrogen moles or in terms of volume hydrogens get adsorbed. So, then in terms of the moles we can convert, and then by doing the back calculation total number of sites we can calculate. Okay. Active metal sites are present. Okay. So, similarly TGA DTA analysis also we can that. So, whatever the materials or the catalyst we have prepared, so we can do the TGA DTA analysis. So, these are the equipment or instruments for the TGA analysis. Here means reference pan, this is sample holder sample pans, and here furnace is there. So, here TGA thermogravimetric analysis or TG analysis, it is called thermogravimetric analysis. So, in TG analysis means suppose in a material, some materials let us say this is catalyst we have, in the catalyst some materials gets adsorbed or some materials occupied, let us say in our nickel catalyst coke deposited over there. So, that may be 0.001 gram coke deposited per 1 gram of nickel oxide catalyst. So, that much means how much quantity of that coke deposited, that easily we can find out by TG analysis. So, here what we have to do. So, here if we pass air or oxygens, so then what would happen, that coke would be oxidized. So, coke plus oxygen, so coke would be CO2 formations would be there, means that much of coke it was theirs, that would be come out in the form this. So, then weight loss would be theirs, initially let us say 100 gram catalyst was theirs, and after this reactions it may be 99 gram. So, how many grams of coke was deposited? So, 1 gram coke was deposited. So, by that way we can measure means by changing the weight loss means quantify, you can like that. Similarly, some materials are there. So, whatever we have prepared. So, if there is weight loss or weight changes versus temperature, this type of graphs we can get, thermograph we can get. So, here y axis it would gives weight loss, x axis would gives temperature. So, at what temperature, see here this material was taken and TG analysis was conducted. So, here you can see a one peak is there, let us say approximately 120 or 10 degree centigrade. So, it may be due to the weight loss of waters, the water may be present in that samples. So, H2O gets dissolved and after that another peak is weight loss is there are 10%. So, 4% approximates each moisture was there and after that another peaks may be 10% that material decomposed. So, some others means this material decomposed at this particular temperature may be 230 degree centigrades and that material decomposed and the gas it is evolved, that may be hydrogens, let us say from here it is, if it is decomposed that would give hydrogen. So, therefore, we can say that the weight loss has started at this particular temperature and that much quantity of weight loss is there for that particular materials. Similarly, DTA analysis also we can do by using the same experiment. So, if y axis that is the temperature difference it would gives and x axis that is the reference materials temperature. So, if any material or catalyst we have that is exothermic reaction, means if we do that thermal treatment, means if we increase the temperatures, either it may be exothermic reactions would be there or maybe endothermic reactions would be there. Means if it is exothermic, then temperature rise of that materials would be there. If it is endothermic, so temperature fall would be there. So, if we are able to measure that very small amount or quantity of the temperature changes during thermal treatment of that material. So, then if delta T, this is the sample temperatures and this is reference material temperatures. So, in this particular experiment two compartments would be there, this is reference materials, this is sample materials compartment. So, here if this reference temperature let us say 600 was there and sample temperature may be 601 degree centigrade. So, this temperature change delta T equals to 1 degree centigrade changes would be there. So, if we are able to measure, so then here temperature rise would be there if it is exothermic and if it is endothermic temperature drop would be there. So, if the natures means depends on that materials we are treating or doing the DT analysis. If this type of natures, then materials is endothermic properties there, if this type of natures, then materials is exothermic. So, that way we can also analyze or the material property also we can study. Next is the X-ray diffractions analysis. So, X-ray diffractions means the crystallite size means whether it is single crystal, polycrystals, the materials that we can do. So, whenever we prepare any catalyst that is in the form of powder form size sets. So, if we do X-ray analysis or X-ray analysis or XRD analysis, so there you can say that we can consider a particles means any materials that has a particular shapes, it may be like this. So, if we go into depth, so we can see that so many grains are there, different grains are there, these are called grain boundary, this is grain 1, this is grain 2. So, if we go in depth of this particular grains, red grain, so there's if we know the atoms are arranged like this, it is orderly arranged, then and one type of crystal is there. So, we can say it is a single crystals, and if blue ones if we take, so there if we see that this is one type of crystals, this is another type of crystals, and the in that materials it is present two different type of crystal, one crystal 2 it is present. So, these types of materials is called polycrystalline material, this is single crystalline materials, and if that materials having those atoms it is distributed like this, it is not orderly arranged. So, then it is called amorphous materials. So, and if it is orderly arranged the atoms, it is crystalline material. So, this is the basic difference is amorphous and crystallines. So, same materials depending upon the synthesis. So, that materials we can make it amorphous materials or maybe crystalline materials. If we synthesize the materials at low temperature, then it would form amorphous materials. If we prepare at high temperature, then it may be amorphous would convert it into crystalline natures. So, that way we can change from amorphous materials to the crystalline materials. So, this is crystalline material, this is amorphous materials, this is single crystal, this is polycrystalline. So, these are the means suppose we have a materials or catalyst that we have prepared. So, if we want to know whether it is amorphous material or crystalline material, or if one particular type of crystal is there or multiple crystal or polycrystalline nature is there. So, if we want to know our material property, so then we have to, of course, we have to do the X-ray diffraction analysis study. So, here's the particular crystallite size also we can find out. So, of that materials from the XRD pattern. So, crystallite size, that is the called L, we can find out average crystallite size that we can find out. So, that is the L. This is Serrar equations, here K equals to Serrar constants, that usually value 9.9. L is the average crystallite size, the materials we have prepared. So, its crystallite size we can find out. Okay. So, it nickel oxide, let us say. So, crystallite size of nickel oxide we can find out. K value Serrar constant we can put, lambda is the X-ray wavelength that we can put it here, beta is the full width at half max. So, if let us say X-ray pattern is coming like this. So, let us say 2 theta value is x axis and y axis that intensity. So, let us say at 20 degree 2 theta value at this particular peak has come. So, at this particular points fully the half max we can find out, that is at this particular point. So, if total height is this I max by 2 is this particular point. So, here this means fully that half max we can find out, that would give actually beta. So, if we know the beta or fully half max in terms of degree, so then we can convert that into radians, this beta value. So, that beta value we can put it here, and theta value we know, that is the Bragg angles it is said. So, at this particular point, let us say if it is 20 degree to 2 theta 20 degree. So, that 2 theta equals to 20. So, then theta equals to 10 degree. So, that way you can find out. So, here's all components we can put and crystallite size of this nickels we can find out using X-ray diffraction patterns. So, here's I am not going to discuss our details about the Bragg's law, that is means how does the X-ray does work. So, these equations one should know. So, this is integer, this is X-ray wavelength, this is spacing between two planes, d spacing, and h scale, that is the Miller indices, and theta, that is the angle between the incident beam and the planes. And see, here's one the results that would come. So, that I am going to discuss. So, here's x axis, that is the 2 theta 20 to 70 let us say, and y axis, that is the intensity. So, if we consider this particular materials having this peak and this peak. So, if we want to find out the crystallite size of this particular. So, here it is very strong, and then it is 58 to 41, then 23 17. So, same materials let us say we have prepared, and here's no peak is observed. So, from the X-ray diffraction patterns we can say that. So, same materials that was prepared by considering different preparation techniques. So, by considering these preparation techniques, the materials that was prepared having larger crystallite size here's compared to the smallers, here's there is no crystallite size. So, maybe at this particular methods the materials we have prepared, it is maybe amorphous, no peak, it does means it is amorphous materials we have prepared, means Fe2 that we have prepared, that was amorphous, and here it is crystalline. So, that way you can also distinguish, means the materials you have prepared by following a particular methods, it forms a amorphous materials, and when you follow different methods, means preparation methods to prepare the same catalyst, it is giving strong peaks, means crystalline natures. So, that and crystal size also or crystallite size also we can find out that way by using, here it is given. So, how 30 nanometers that has crystallite size. So, beta value that was calculated at 2 theta value. So, at theta equals to we can put 80 and beta equals to 0.26, 0.26 equals to this much of radian. So, we can put it here, K value is this, lambda value is this, then average crystallite size we can, or crystallite size we can find out, and similarly all points we can find out, and average crystallite size also similarly we can find out. So, okay, so you can find these plots in this journal or article. So, we can get it. Okay. So, similarly means TEM same also is there. So, this is another characterization techniques or electron microscopic it is said. So, if we means normals, if you see any powder samples, it is in the form of powder, small particles is there, but if you want to go enlarge that means image and internal or external structures of that materials if you want to see, then we have to go for electrons microscopic or same or TEM image you have to collect, and then we can analyze those materials or objects what we have. So, these are the instrument details, not going to discuss details. So, you can find it. So, how does it work actually? So, this is the basic means summary of means two microscopic and what kind of informations we can get from TEM and what kind of informations we can get from SEM. So, depth relations TEM is better. So, 1 to 10 nanometers, here 10 to 100 nanometers, here lateral resolutions is 0.1 to 1 nanometers, here 1 to 10 nanometers, here magnifications is that much, and here it is up to this, and here 2D image we can get from TEM, here 3D image we can get, here sample preparation is required means very thin film formations or very thin means samples we have to prepare as if through that samples means lasers or electron beams may pass. If it is that much thick, so then beam would not pass. So, as thin as possible for TEM analysis, but SEM analysis does not require like that, but if sample is not means electron conducting, so then we have to make a coating means conducting elements coatings over the samples we have to do to get a image. So, from the TEM analysis we can get TEM image, SAED interpretations means atomic and crystallographic information, particle size. So, these are the informations we can get from the TEM analysis of the samples, and same we can get same image analysis and EDS analysis. These are the informations we can get for this particular systems. Okay. So, from the instrument how does it work? So, details will get anywhere. So, here I am just showing means if electron beam is there and this is the sample. So, through that the electron beam passing through the samples transmitted electrons or beams if we get in the form of image. So, then we get TEM, and so when it is backscattered or secondary electrons, that is after interacting with the materials or samples, then backscattered electrons, secondary electron that would be collected in the detector. So, then image will get, that is the SEM image. Okay. And some light or X-ray also would be emitted. So, if we get that, so then EDS analysis also we can do with the help of same analysis with the same image, EDS also we can get. Okay. Here you can read it, but I am not going to discuss means how means the electron beam interacted with the cell electrons, and so how the image we are getting, and others X-ray or means EDS analysis we are getting. Okay. This is the same image, and from the EDS analysis you can get means a particular elements present in that catalyst and at what percentage presence from this EDS analysis you can get, and this image you can get for that particular samples. Okay. And you can analyze those samples, and here I can showing this is the fresh catalyst from one articles we have taken this is fresh catalyst. When that catalyst was means studied for a particular reactions, after that so many CNT formations was there. This is used catalyst, this is also another fresh catalyst. So, in this catalyst also CNT formations is also there. So, here CNT diameter is greater than this. So, in this catalyst CNT is narrow diameters, here CNT formation is little bit larger diameter formations is there. So, this type of interpretations we can do. So, now TEM image analysis or from the TEM's SAED analysis we can do. particle size analysis we can do. Means I said that when X-ray diffraction study we have do, we have said it is a single crystal, it is a polycrystalline, materials may be polycrystalline or single crystalline. So depending upon that material, so SAED image will comes, and by that we can get either these spots we can get in the image, or you can get this type of ring structure. So it depends, means when it is spots it means a particular single crystals is present. So when it is ring type of this there, then multiple means crystal presents in that sample. So by that we also the samples we have prepared or catalyst we have prepared, so we can distinguish and we can classify that materials we have prepared and why that particular materials is giving a better result compared to the other, that way we can analyze. Okay. Similarly, particle size also we can measure or we can calculate using the TEM image analysis also, means from this. So individual spots we can count, and based on that means some factors we have to angstrom and pixel, some factors we have to find out, and we have to count the total number of pixels, and based on that the particle size also we can calculate. That we can compare with the X-ray diffraction analysis also. There also we are getting the crystallized size, and here so we can correlate, we can match them. Okay. So if spectroscopy study is also there, means that is we can do also, but I am not discussing that. Okay. So FTIR spectroscopic is there. If suppose you have a materials having dipole moment change, so then we can means get that spectra that is IR active. So this is interferometers. So how FTIR spectroscopy does works by inside when sample we have placed. So movement of the mirrors would be there, one moving mirror, another stationary mirror is there, and here beam splitter is there. This is the source from IR source, and this is detector. So here is the sample. So through that we can get in the recorder or computers, we can get a spectra, wave number, centimeter inverse, and intensity we can get. Okay. So with that help of spectra. Okay. So that we are not going to discuss more details, so you can study it. So there are means asymmetric stretching, symmetric stretching, bending is also there when a molecule is having means different type of freedom. So stretching formation when means IR is inserted over that materials, that particular type of vibrations would be there in that molecules or compounds, and depending upon that asymmetric stretchings, symmetric stretchings or bendings, that type of things we can get, and we can analyze that spectra. Okay. So how to calculate the wave numbers, means when we are calculating the stretching frequency for a particular compounds and particular bonds, here you can see that CH bond suppose we have. If you want to know the stretching frequency of that, so these equations we can use. Here bond is single bonds, then force constant we have to use this, and reduced mass we can find out, and then we can substitute here mu, and then within that range we can get that vibrations of CH bond of that particular compounds or materials present. So that way you can similarly some other compound bonds are present, functional groups are present, that we can get with the help of IR spectroscopy. So here's stretching frequency and functions group is given, and various modes of IR measurement analysis. Transmissions mode we can either in the form of liquid cuvette we can use, or maybe we can make a pellets. With the pellets, if IR is passing through this, so this is detector, detectors we can get that IR that is passing through the samples, and based on that the spectra will get. And here DRS mode also we can do the analysis, specular reflectance we can do that, ATR mode of analysis also we can do that. So many way we can do that IR analysis of the spectra we can get for that materials we have. Here this is the background spectra. Always any materials, if you want to do the study for FTIR spectroscopy, you have to take first a background spectra, and this is sample spectra, absorbance against wave number. So the sample we can do the analysis. Okay. So, this is the spectra we have to analyze, and this is few examples I am showing. Next, Raman spectroscopy. So, I am not going to discuss about the detailed theory of that. So, this is inside of the Raman. So, how the source, laser source, samples, other things are there. Okay. So, here this is the means if Ramans and FTIR. So, symmetrical stretching, asymmetric stretching, bending is there. So, if a material is Raman active, symmetrical stretching is there. So, then the material should be Raman actives, but Raman IR inactives. If molecules having IR actives, then molecules must have means asymmetric stretching and bendings. So, means if a compounds symmetric stretching, asymmetric stretching, bendings, 3 type of means vibrations we can get. So, out of that few informations we can get with the help of Ramans, and these are the informations we can get means from Ramans IR. So, let us see molecules having 3 different vibrations. So, from these IRs we can get, that is the symmetrical stretching, new one that we get, and if asymmetric stretching is there, that we get from IR, and asymmetric stretching, and bending is there. So, then bendings we can get from IR. So, partial informations we can get from IR and partial informations we can get from Ramans. So, once we combine those things, so then overall structure of the materials we can get. Similarly, UV spectroscopy is there also, that also we can study. Okay. X-ray XPS also study we can do. So, that is also there. So, to analyze that materials. So, this is the survey spectra for a materials. So, this type of, when if we analyze let us say these materials we have or catalyst we have prepared. So, if we want to do XPS analysis, this type of survey spectra we will get. X axis the binding energy and y axis the intensity we can get, and let us say here iron, manganese, magnesium, alumina, oxygen are present. So, magnesia you will get it here, alumina you can get it here, and carbon is also there, that will come by default. So, oxygen is there. So, manganese is also there, iron is also there. So, by that individual range of binding energy if we know, so and if we analyze then and compare one sample to another samples, by that way what are the means components are present, means states means so what kind of particulars means materials is present, that we can easily quantify or identify. Okay. Means with the XPS we can find out chemical state identifications, a quantitative analysis including chemical state difference between samples, oxide thickness measurements. These are the things we can find out with the help of XPS analysis. Then gas chromatography, that is when we conduct any reactions. So, then that is required to find out the concentration of the individual components, means product components. So, with the help of GC we can do that. So, this is means looks like say GCS means how does it look like. This is GC column that would be placed here, and this is inlet points, this is detector points, and this is oven. Okay. So, this is switchboard is there. So, this is analytical techniques. If you look at this is schematic diagram. So, this is carrier gas, maybe nitrogen, argon, helium we can pass, that would be passed here, and it would reach through detector to we can get this type of spectra. Okay. So, if we inject some sample, let us say we have mixture of hydrogen, CO2, CO. So, these 3 components are there, 3 different components have 3 different mass, molecular weights are different. So, if we consider this when it is injected here, so it would follow these columns and then it would come out through the column and reach to the detector, and detector individual component will detect and corresponding concentrations we can get. Here hydrogen, this is CO2, this is CO, that way we can get. So, this is actually running track. So, if we start the 3 component has started running from here, but due to their means polarity, non-polarity, molecular weights, their velocity would be different, means like a running track. If we want to complete 100-meter runs by 3 different peoples, they reach the destinations at 3 different times. So, like this here it would reach 5, this is time. So, 5 seconds, 10 seconds and 15 seconds. So, 3 molecules takes different time to reach from here to here, same distance to cover. Okay. So, by that way one components will come, and with the help of detectors we can quantify how much quantity of individual components are present. Okay. This is for simple gaseous components. With the help of gas chromatography we can identify or quantify, but when means larger molecules or very liquid molecules are there, so many compounds are there. So, with the help of normal GC and packed column we cannot find out or we cannot identify. So, then we have to go for much more advanced technology, that is GCMS we have to use. So, with the help of this is means here's GC and that GC both are same, but columns are different. Here additional things are there, that is the mass spectroscopy, or with the help of there's in that GC here the detector may be FID or TCD was used. This detector are not much more sensitive as mass spectroscopy or MS detector. So, here's individual components we can find out, this is GC, this is MS, both are coupled. So, here from the GC individual components will come out and one by one enter into the mass spectroscopy, and then it would analyze with the help of mass spectroscopy, and then at different fragments will forms and mass by charge ratio will gives, and that with the help of that we can quantify that which component is present and how much quantity of the present, that easily analyze. So, let us say this is m by z value for benzene. So, if we analyze with the help of GCMS that benzenes, so benzene's molecular weights, that is different fragments will come C 6 into and 6 multiplied 1, 78 molecular weights. So, benzene's molecular weight is 78. So, here you can see m by z is this and y axis that intensity. So, when benzenes will be detected, so highest the molecular fragments that is coming, that having molecular mass m by z, that is 78. So, with the help of this we can say that compound is benzene present, and this spectra will MS spectra will get, that is due to benzene. So, like that if any other compounds are present or in that liquid mixtures and come out with the help of GC MS analysis, so then individual components we can get individuals m by z ratio or mole fragment molecular fragments. So, with the help of that we can identify, library is also there in that system. So, with the help of library we can match the spectra and that available information. So, if it is matching close to our experimental spectra and available spectra, so by that way you can identify which particular unknown compounds are present in that means products. Okay. So, thank you. So, today is up to this. So, I think this course is over. So, thank you.